Welcome back. We are starting our fifth theme on the ordinary differential equations, and we also completed 28 lectures, which is roughly the half of the lectures that we are planning to have for this course. So let's begin the ODEs right away. So I hope you are able to see the slides now. So OD is, meaning for an engineering student, there is really no need to give any motivation for studying ODEs, or ordinary differential equations. These model problems in science and engineering that involve the change of some variable with respect to another variable, wherever, just to give you an idea, whenever there is a mechanics involved, there are differential equations involved in that study. So that's what we have. And what we have to also take into account is some initial value of the solution that we expect. So the solution is supposed to have an initial value property. So that's why these differential equations are called initial value problems, because we not just state a differential equation which your function should satisfy, but we also state an initial value for the function. Now what happens is that these differential equations which model our real life situations, they are very complicated, and so it is typically impossible to solve them exactly. So there are two approaches that one takes. In the first approach, what we do is that we change the differential equation itself. We change it slightly so that we reach a differential equation which can be solved, and then we hope that the corresponding solution will give you an approximate solution to the earlier problem, to the original problem. This is approach number one. Second approach says that we don't change the differential equation, but instead of solving the differential equation in an exact way, we give an approximate solution. So this is the second approach, which is a much better approach. This is one that is taken most commonly because it gives accurate results, and its error information can also be studied in a realistic way. This is why we are more into studying the numerical ways to solve the ODEs, the initial value problem, the numerical methods to solve the IVPs. One drawback is that our methods will not give a continuous solution. What it will do is that at various points, we are going to predict the approximate values of the solution. That's what we are going to do. So these are the points which are called mesh points, and at these mesh points we predict the approximate solution, and then for other points we use the interpolation methods that we have learned so far to get the actual function. This is what we are going to do. The basic material that we have to learn is something which is which centers around this thing called Lipschitz condition. So let's understand this. So whenever we have a subset D sitting in R2, so we have a subset of the plane, a function t comma y is defined on this subset. We say that this function satisfies a Lipschitz condition in the variable y if there is a constant L positive such that for every t, the f of t y1 minus f of t y2 is less than or equal to L times y1 minus y2. So the difference between the function values for any t, the function values, the difference between the function values at ty1 and ty2 for any fixed t should be less than or equal to capital L mod of y1 minus y2. This is what is called a Lipschitz condition, and then this capital L is called the Lipschitz constant for our function f. Okay, so this is a very important condition. It will show up at least twice in our lecture today. So the theorem that we are going to state here now says that if you have this particular subset, capital D, which is Ty, where T varies from A to B and Y varies over the whole real line. So it's a vertical strip that we are looking at, and Fty is a continuous function defined on this vertical strip. Okay. Now, if you have that your function f satisfies the Lifshitz condition on this capital D, then this initial value problem has a unique solution. So whenever your function satisfies Lifshitz condition, the initial value problem has a unique solution. You can prove that there is a solution which is a unique solution because you have also specified the initial value. Typically what happens is that the differential equation will have solutions which are given by which also involve a constant which is to be specified. But once you have this initial value, then the constant is specified and therefore the solution becomes unique. So this is the very first application of having Lifshitz condition. Whenever you have a Lifshitz condition, then your IVP, the initial value problem, is guaranteed to have a unique solution. Yeah, so now we have to also consider something called as well-posed problem. So let's see why we have to think about it. So initial value problems are obtained by observing physical phenomena. Okay, and they generally only approximate the true situation. Typically, there is a situation which is given to you, some real life situation, and you want to convert it into some equation by putting in some numbers. And whenever we use numbers, there is always some approximation. There could be a round off error or there could be a calculation error. So what happens is that there might be small perturbations in the problem itself. So what we would want to know is whether our problem is well posed in the sense that might be some small perturbation in the problem. Does it introduce correspondingly small changes in the solution? That's what we want to know. It should not happen that whenever you have small perturbations in the problem, the resulting change in the solution is very large. We don't want that to happen. If that doesn't really happen, the small change in the problem results in a small change in the solution, then we say that our problem is well posed. Okay, so let's make it specific. So of course, this is because the round of error typically does take place. So we say that an initial value problem is well posed if, first of all, you have a unique solution to your initial value problem, and an initial value problem obtained by small perturbations also has a unique solution. This is what we mean. But this second condition has to be made slightly more precise. So we have to call upon our friends epsilon and delta to make it more precise. And this is how we do it. So we consider this initial value problem, which is y prime t, which is also dy by dt equal to f of ty. T varies from a to b. And the initial condition says that ya is alpha. Okay, this is our initial value problem. We say that this is a well-posed problem if a unique solution yt to this problem exists. And now let me just state the whole statement and we will try to understand the statement. And there are two constants, epsilon positive, epsilon not positive, and k positive, such that for any epsilon that you choose which is less than this epsilon naught, any positive epsilon less than epsilon naught, and whenever you choose a delta t which is continuous function on the interval ab, whose sup norm, whose maximum value is bounded above by epsilon, and you choose one more delta naught which is less than epsilon, then this modified initial value problem has a unique solution. Okay, so k so far has not come. Whatever we have said here from all this up to here doesn't figure doesn't contain our k. The k will come now. That satisfies mod zt minus yt is less than k epsilon for all t in AB. This is the statement, and let me now try to explain this to you. What we are having is that, first of all, that our initial value problem should have a unique solution. And now we are making small perturbations. In our initial value problem, the perturbations can be made in two ways. You can change the differential equation itself. So you will have a dy by dt equal to f of ty plus something. And that something should not be very large. So what we are looking for is that this function delta t is a function whose modulus is less than some fixed epsilon. So it's not very large. And secondly, we are also changing the initial value again by a number which is very small. Okay, so these are the two things that we are changing. So what we say is that there is an epsilon naught bigger than 0 such that whenever you choose any epsilon less than this epsilon naught, so up to epsilon naught, you have the whole range, and you are allowed to change your initial value as well as the equation by something which doesn't go beyond a fixed number in this range. Okay, so therefore we have now a positive epsilon within the range 0 to epsilon naught, and given this epsilon we choose two things. We choose a continuous function delta over AB whose modulus is bounded above by epsilon, and we also choose a real number delta naught which is less than epsilon. Okay, so there should be a mod also for delta naught. Then we have made two changes. The delta t is used to make change in the differential equation, and delta naught is used to make change in the initial condition. Even after having done this, there is a unique solution. That is what we demand. And moreover, this unique solution zt or zt should not be too far away from the initial value problem solution to the original initial value problem. So the unique solution yt to the original value problem, that and this solution to the new modified initial value problem, they should not be too far away. It is allowed to be slightly away from epsilon, and you may not expect that the whole thing is less than epsilon all the time, but it should be bounded above by some k times epsilon, where k does not depend on epsilon. K is something which is independent of all epsilon. You are allowed to choose epsilon anywhere between 0 to epsilon naught, and this k is something which is fixed. So if you have an epsilon naught which is a range for this epsilon, and you have a k such that you have the two solutions, the perturbed values, the perturbed problem solution and the original solution, they don't go too much apart from each other. The distance between them is less than k epsilon, and then you have this epsilon with which you have modified these differential equations and the initial values. Again, it should have a unique solution such that it doesn't go too much away from the solution to the original problem. If that happens, then we say that our problem is well posed. So initially, we saw that our Lifshitz condition ensured that there was a unique solution. Once you have a unique solution, then you can hope to solve and you can try to get some approximate solutions to that. But then we observed that there could be some perturbations because of our own limitations. We do round off errors, we do calculation errors. We are not perfect people. So our problems can be perturbed, and even after having these perturbations, we are not perfect, but we are looking for something, which is greedy. We are very selfish people. So even after understanding that there could be perturbations, we want that the solutions to the perturbed problems should not be too far away from the solution to the original problem. This is what we are asking for. Now, is there a result? Is there ideally some theoretical result which will say that if this happens, then the problem is well posed? If such a thing is there, then we will be very happy, and indeed there is one such thing. So, all right, so let me say something about the perturbed problem. The perturbed problem which is the specified problem above, is called perturbed problem associated with the original problem. Now, it assumes the possibility of an error being introduced in the statement of the differential equation. So we are changing our dz by dt equal to f of tz plus delta t. So we are changing that function on the right hand side, as well as an error delta naught being present in the initial condition. So it assumes two such things. And numerical methods are always concerned with solving a perturbed problem, because any round of error introduced in the representation does perturb the original problem. So we have to look for perturbed problems, and therefore we really wonder whether our problems are well posed. If the problems are not well posed, there is little reason to expect that the solution to our perturbed problem will give you a nice approximation to the solution to the original problem. So having a problem well posed is something that is really, really very important for us. So there is a condition which ensures well posed property. So this is the theorem that we are going to state. Suppose our D is again given as above. It's the vertical strip which goes from A to B on the x-axis, and then the y values are assumed to be any real number. If you have a continuous function which satisfies the Lifshitz condition in the variable y on the set D, then the initial value problem is well posed. So this is the second instance that the Lifshitz condition has shown up. Of course, we are also assuming that our function f is continuous, but that is something that we have been assuming from antiquity. So that is something that is very natural for us. But Lifshitz condition is a new thing, and that condition has not just ensured that our initial value problem has a unique solution, but it also tells you that a small perturbation in the initial value problem gives you still a unique solution which doesn't go too far away from the solution to the original problem. All right, so now in the remaining time, we are going to study some numerical methods. We begin with a method called Euler's method. So Leonhard Euler, a Swiss mathematician, I believe, from a very long time back, and he developed a very basic method to solve the differential problems, the equations, the initial value problem. It's really the most elementary method, and this is typically not used in practice, but the simplicity of this method can be used to illustrate the techniques that we will see later. The more advanced techniques that we will see later, they will be illustrated by the Euler's method. So Euler's method is a stepping stone, and it's a very important method. You will see that there are some very basic ideas that go into this method, and it gives reasonably good approximations. So what we want to do is that we have this well posed initial value problem, and we want to get approximations to the function y at various points. So we are not going to get a continuous solution, but we generate approximations at various values, and these are called the mesh points in the interval AB. So at various t, we are going to get the values for yt. That's what we are going to do. And once the approximate solution is obtained at these points, then we, as I said above earlier, some approximate solution can be found by using the interpolation method that we have learned, and we are now quite comfortable with these interpolation techniques. So what we do is that first of all we choose a positive integer n, and we select equally spaced mesh points. So we have interval a, b, and we select some nodes. In our language of interpolation, we select nodes which are equally spaced. Okay. Now the common distance is h, which is the distance between any two successive nodes, and it's also b minus a upon capital N. This is called the step size. Okay. So we are going to use Taylor's theorem to derive Euler's method. So what we have to do is the following. Suppose yt which is the solution to the problem, it has two continuous derivatives. That means yt has a derivative which is continuous, yt derivative is again differentiable, and that is continuous. So we are assuming that y is twice continuously differentiable on AB, so that we can use Taylor's method. And the Taylor's method will give you that y of ti plus 1 is yti plus ti plus 1 minus ti. So we are using the Taylor's theorem at ti, and we are getting the value at ti plus 1. Okay, so that value at ti plus 1 is yti plus 1 is equal to yti plus ti plus 1 minus ti y prime ti plus ti plus 1 minus ti whole square upon 2 y double prime xi I at some point xi I between ti and ti plus 1. But the common distance, the step size is h, so we get that this is simply yti plus h y prime ti plus h square by 2 y double prime xi I. And as is very common now in this course, we are going to ignore the error term. So this h square by 2 y double prime xi I, that's going to be ignored, and we get yti plus 1. Okay, so first of all, instead of y prime ti, because the y satisfies the differential equation, we will simply write f of ti yti. All right, so on the right hand side, these are the terms which we can compute using the ti node, because yti has already been computed. We are now computing y of ti plus 1. So yti has been computed. H is anyway the step size that we know. The function f is given to us when the initial value problem is posed. Then it is already dy by dt equal to some f of y comma t. So that function is also given to us. Only thing that we don't have is this y double prime at xi I. So let's ignore that. And what we do is that we compute this wi, which is an approximation to yti, by deleting the remainder term. So this h square by 2 y double prime xi I will be ignored, and we simply compute the wi, which is an approximation. Here we have an equality in the Euler's method. And if we ignore the remainder term, then what we get is an approximate value. So this approximate value is the one that we are going to consider. What is going to be the initial value? Of course, the initial value is given to us to be alpha. So W naught has to be alpha. And then Wi plus 1 is Wi plus h f ti comma Wi for I bigger equals 0. Okay, so this is how we are going to consider these things. Of course, observe that W naught equal to alpha is the exact solution. W1 is an approximation to y of 1. And if you were using y of t1, you can hope to compute y of t2 in a better way. So if you ignore this h square term, but if you know what is y of t1 exactly, then you can get a good approximation. Your W1 is already an approximation to yt1. And therefore, by putting that value for W1 in that equation to obtain W2 will give a slightly loose approximation to yt2. And then that will give a further weaker approximation to yt3. So it will, you will see that the approximations tend to be slightly worse as as we go further and further in the nodes. Okay, so let's see an example first. We will illustrate it by means of an example. We consider this initial value problem, y prime equal to y minus t square plus 1, where your t goes from 0 to 2. And of course, we assume, as always, that y goes from minus infinity to infinity. Y0 is given to be 0.5. Okay, so this is the initial value problem that we have. We will not check the Lifshitz condition, but we will assume that this is a well-posed problem, and we start solving it. Let's suppose that we want to approximate y2. Okay, so instead of approximating the whole function, we just approximate y at the other endpoint. That's what we are going to do. We are taking the step size to be 0.2. So we go from 0 to 0.5. I'm taking it to be 0.5. 0.2 will come later. We go from 0 to 0.5 to 1, 1.5 and 2. These are the small number of steps that we are going to look at. F is y minus t square plus 1. So we start with W naught, which is 0.5. That's the initial value. W1 will be, remember, it's the W naught plus h f of t naught W naught. Now at W naught, t naught is 0. So we will have it to be y, which is W naught minus t naught square, which is 0 square plus 1. So this turns out to be 0.5, which is W naught, and 0.5 is outside here, so that remains here as well. Then 0 square is 0 and 1 plus 0.5 gives you 1.5, and so the answer is 1.25. This is W1. W naught is 0.5, W1 is 1.25, W2 is 2.25, W3 is 3.375, and finally Y2, which is W4, is 4.4375. This is the approximate value for Y2 of the function that we are going to look at. Now geometrically, so I told you that Wi is already an approximation to Yti, and we are going to put that in the equation to compute approximation for Yti plus 1. But it's not too bad because our problem is well posed. So we will, what we have done is that we have modified, as you have gone taking approximations, we modify the problem, but the modifications in the problem, the perturbations in the problem are very small, and therefore it is expected that the solutions that we obtain, they are not too far away from the original solution. That's what we have here. Okay, so this method is still a legal method. All right. So now let's take a bigger value of capital N. Here we had n equal to 4. Capital N was simply 4. We went only up to W4. Let's take a larger value for n, which is 10. And now I will also let you know that the solution, the original solution, is t plus 1 whole square minus 0.5 e power t. So what we are now going to do is that we will compute the approximate solutions and we will compare them with the actual values of this original solution y of t. Okay, so h is 0.2 because our distance is 2, it's from 0 to 2, so it is 2 upon 10, that's 0.2. Ti is going to be 0.2 I. Remember, those are equally spaced nodes. And we have W naught, which is 0.5, the original initial value. Then Wi plus 1 is Wi plus h, Wi minus Ti square plus 1, which is the function involved in the differential equation, initial value problem. And we will simply put the various values. So here h is 0.2, Ti is 0.2 into I, so Ti square will be 0.04 into I square plus 1. And simplifying this will give you 1.2 times Wi minus 0.008 I square plus 0.2. This is the formula for Wi plus 1 from Wi. So we will get that W1. We started with W naught equal to 0.5. If you put the W naught value here, you can compute W1 from this equation, which will be 0.8. W2 is 1.152 and so on. And the approximate values and the actual values can be compared using this table. So we see that at the initial value, we have no difference at all because the initial values are the same. Then as you go on taking various values for Ti, the errors start getting bigger and bigger because you are perturbing the problem itself at each step. But notice that the approximate value 4.8657845 is much better than what we had for our initial illustration of Euler's method. So when we had h equal to 0.5, the approximate value was 4.4375. Whereas for this smaller step value, it is 4.8657845, which is much closer to the actual value. So, of course, if you take h smaller and smaller, then you are going to get much better approximations. That is quite clear. However, we also saw that the error grows slightly as the value of t increases. The initial values are same, so there is no error, but the errors do occur at various steps, but they don't grow too much. The errors also do not grow too much. That is something that we should notice. So this is the error growth is a controlled error growth. And this is a consequence of what is called the stability of Euler's method. Euler's method is one of the very stable methods. And what it ensures is that the error is growing in a way which is weaker than the linear manner, meaning it will not grow worse than the linear manner. So this error analysis of Euler's method and maybe some other methods will also be studied in the next lecture. So next lecture will be our 30th lecture, and we will continue with the study of our differential equations. So see you then. Thank you.